Hello guys. Hello. So we will start from where we finished off last time. I hope you are uh, liking the lectures of Dhairya ma'am. So she is kind enough to share her experiences on combinatorics, and she has already completed 3 lectures. This is the previous year lectures, and you must have seen that we have really accelerated our live IOQM English course now. uh, and we will be completing the syllabus very fast, right? Okay, so let's get going. So my name is Prashant Jain, all India rank 42, JEE 2008, AIR 5 ISI B stat 2025. It was 2025, not 2005. So this is our JEE result and this is our ISI result. I want you all to see the results of ISI, which is completely mathematics based examination. ISI is Indian Statistical Institute. We have got all India rank 24, 57, 59, 81 and 84. So these are 5 ranks which we have. All the learners are classroom learners. All the learners are classroom learners. Okay. Okay. This is our JEE main results. Yes. And this is something which you all should take a note of. We are starting a course on 25th of June. It's a fresh course. It will start from basic. Idea is to get 30 to 40 marks in IOQM. Obviously, it will not go to that level of IOQM because it requires complete year to complete. You can use code PJ Live and take the subscription. It will be done under my mentorship, obviously. Right? Yes. Okay. So we have already done this. I think we have done till how many questions we have done? Do you remember, guys? How many questions we have done? Do you remember? Do you remember, guys? How many questions we have done? How many questions we have done? Do you remember? I do not remember. I think we have done till 2019. We have done all questions of 2019. We were to start from 2020. That is at what I feel. We have to start from 2020. We have to start from 2020, if I remember. Yes. 2020. Where is 2020? We already did this. Pre-Armor 2018 was something very amazing. Where is 2020? Just a second. 31. 31. We have done till 31. Okay. Yes. 31 we have done. This is 32. This is still 2019. We were to do from 2020. Yes. Okay. So we'll start from this question. Right? A number n in base 10. See, like the rules is very simple. You have to pause the video. You have to attempt. If you have not already attempted it, I hope you have attempted the questions. Then you will see my solution. A number n in base 10 is 503 in base b, which means 5b square plus 3 and 305 in base b plus 2. B plus 2 whole square plus 5. Right? This is the equation and this is how you will get the b. What is the product of digits of n? So let's find. First of all, we'll find base b. So what is this? 3b square plus 4b plus 4 plus 5. Okay. 5b square plus 3. So that's 2b square. 12b is minus 12b plus 3. What is it? 12 plus 5 is 17 minus 14. So it's b square minus 6b minus 7 equals 0. So b is 7. B is 7, guys. Okay. So b plus 2 will be 9. So what is this number? 5 into 7 square plus 3. This is the decimal number, right? So this is 49 times 248. So 248 is, the product is 2 times 4, it is 64. 64 is the correct answer. I hope I am making sense, right? I hope I am making sense, right? Sir, please request, answer the question, Hindi, Prashant Jain or English course, which see like English course is live, right? But if you are comfortable in Hindi, you should focus on the lectures which we are premiering on Friday. I've already told this thing multiple times. Like skip PNC, I would say. Don't skip geometry because geometry will have lot of problems. Okay. Done. Let's move on to the next problem. What is the least positive integer by which 2 to the power 5, 3 to the power 6, 4 to the power 3, 5 to the power 3, 6 to the power 7 should be multiplied so that the product is perfect square? Product is perfect square. This is a product. So first of all, identify full powers of 2. So say like this is already a perfect square. This is already a perfect square. So just remove these two. Okay. So you have 2 to the power 5, 5 to the power 3, and then 6 to the power 7. So just write 2 to the power 12 here. Remove this as well. Then 3 to the power 7. You simply have to multiply by 50 to make it a perfect square. To make it a perfect square, you simply have to multiply it by 50. Isn't it? Content wise, both the contents are same. Both the contents are same. If the person is same, the content will be same, right? Right? Perfect. 15 is the correct answer. Now, a 5-digit number in base 10 has digits k, k plus 1, k plus 2, 3k, k plus 3 in that order from left to right. If this number is m square for some natural number m, find sum of digits of m. Right? Right? So, see, it is a 5-digit number. So, 10 to the power 4 into k. This number is this. Right? 10 to the power 3, k plus 1. If I write it in expanded form, right, plus k plus 3, right, this is the number. Okay, this is the number n. Okay, and it is a perfect square. So first of all, evaluate it. This is 10,000 k plus 1000 k plus 1000 plus 100 k plus 200 plus 30 k plus k plus 3. So I can say that this is 10,000 plus 1000 k. This is 1 1 1 1 1 1 3 1k plus how much? 10203, right? 10203. Okay, 10203, isn't it? Are you getting my point? Are you getting my point? Which lectures of you complete sequence and series and quadratic equation? See for my JEE lectures. Right? Okay. Now this is a perfect square. This is a perfect square. Okay. This is a perfect square. Now just see, k can be what can be k? K can be, see like k is a digit, right? K is a digit. So k can be 1. Then this become 1, 2, 3, 1, 2, 3. In fact, we should not have done all these things. It's a very simple case, right? K has a very limited value. 1, 2, 3, 3, 6. This is one number, right? If k is 2, 2, 3, 4, 6, 5, it is rejected, it cannot be a perfect square. Then 3, 4, 5, 9, 6. Right? So this can be a perfect square, this can be a perfect square. Right? This can be a perfect square, this can be a perfect square. So just see if it is a perfect square. 1, 2, 3, 3, 6. How do you do it? This, like this. 1, 1, 11, right? 1. So it can be a perfect square of 114, right? 114. So it will be how much? 4, 5, 6, right? Into 114, 114. So this becomes 12996, 12996. So this is not, this is the number, right? This is the number. And you just have to simply factorize it. I think 34596 is the number. 34596 is the number, right? Now you have to take square root of it, right? Take square root of 34596, right? So 1, right? 245. Then 1, 2, 3, 5, 7. What will be, what it will be? 29 nines are 261, 28 eights are 204, 6, 224. Right? 3, 6. What is it? 2196. Right? I think 186. 366 into 6. Right? 6, 3, 9. Yes. 2196. So it becomes 186. M becomes 186. You know how to calculate square root, right? You know, guys, how to calculate square root, isn't it? You know how to calculate square root, right? I just assumed that you know how to calculate square root. Okay. Perfect. Perfect. 15 is the correct answer. If you add the digits of 186, it will be 15. Find sum of all positive integers n for which 2 to the power n mod 2 to the power n plus 5 to the power n minus 65 is a perfect square. Right? Again, this is IOQM 2021. Mod 2 to the power n plus 5 to the power n minus 65 is a perfect square. Okay. Mod 2 to the power n. Right? So, let's calculate F1. 7 minus 65 is 58. F of 2, 29, 36. F of 3, it will be F of 3 is, then it will be positive only. 125, 125 plus 8. Plus 8 is 133 minus 65, right? So it will be 68. F of 4, 16 plus 625 minus 65 is 576. F of 5, right? If I do F of 5, 32 plus 3125 minus 65, unit digit will be 2, right? So, if I see closely, the unit digit of this is always 0. So, n can be either of the type 4n plus 2 or 4n, right? 4k plus 2 or 4. Because the unit digit cannot be 8. So, for example, in any perfect square, unit digit cannot be 8. Okay. 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 So, this is one reasoning. And then the next reasoning is, which we have to do, like if you take f of 6, just take f of 6. It is 64 plus, what is 5 to the power 6? 5 to the power 6 is, just a second, 5 to the power 6 is 15625 minus 65. This becomes, eventually I'll get 4 here, 15560 plus 64, 04, 24, 65, 15624. 15624. Yes. Would have simply 64 minus 65 is 156. So obviously it's not a perfect square. Find sum of all. See, like basically I think only this and this 2 and 4 will be the answer. 2 plus 4. Obviously we'll have to do some reasoning. Right? I think we have to do some reasoning to it, but this is largely the answer. Just a second. Yes. I'm just, yes, this is the 36. Which problem was it? I think it's chapter number 4. I'm just finding the answer key. Yes. Yes, this is the answer. 6 is the only answer. Correct. Now, moving on. The product 55 into 60 into 65 is written as product of 5 distinct positive integers. What is the least possible value of largest? See, like it is written as product of 5 distinct positive integers, least possible value of largest of these integers. Right? So let's 11 into 5, 12 into 5, 13 into 5. Right? Now 11 and 13 will be together for sure. Right? Then we can have 12. So one possibility is to have 1 and 5 into 11 into 12 into 13 into 25. Right? 5 into 11 into 12 into 13 into 25. Right? This is one possibility. Okay. Now, can I reduce this number? That is my whole concern. So, if I take 4 from here, right, and take 5 from here, so I get 15. So, 5 into 11 into 13 into 15 into 20. Right? Basically, this is 300. This is my largest number. I don't think I can go lower than this because these three are anyway prime numbers. right? These three are anyway prime numbers. I don't think I can go lower than this. So 20 is minimum of the largest value. 20 is minimum of the largest value, right? Perfect. See, like in this problem, right, it has to do with congruence. So you have to take these two cases, right? And then you have to analyze the last two digits, right? It has to do with last two digits. In this case, last two digits have to be seen. The last two digits after some time, it will be such that there will be no perfect square of this, of those possible combinations. Okay, got it. Right? How many numbers have exactly 4 positive divided factors, right? Are also considered as factor of n. So basically this we have already done. It is either of the type PQ or PQ, right? So how many 2-digit numbers? So it will be 3 to the power 3, 27. This is the only number which has 4 divisors and which is of 2 digits, right? Other than that, it should be product of 2 primes. So with 2, you take 5, 7 until 47. With 3, you take 5, 7 till 31. With 5, you take 7, 11, 13, 17, 19. With the 7, you take till 11 and 13. Right? That is it. That is it. So in total, there are 30 values. In total, there are 30 values. 29 from here, 1 from here. Okay. It's a very simple thing. It is very simple thing. Perfect. 30 is the correct answer. Yes. Now, let's see this. For a positive integer n, let n denote the perfect square integer closest to n. For example, 74 is 81, 18 is 16. If n is the smallest positive integer such that 91, 120, 143, 180, and then this is n, is 91 into 120 into 143 into 180 into n. Right, this is given. Find sum of squares of digits of n. Okay. So see, like, what is this? This is 100. This is 121. This is 143, right? This is 144. It will be 169 into this, right? So we have to evaluate it first, right? What are we getting? So see, this is 11 square and 13 square. So I have 13 here and 13 here. So 7 into 13, 11 is getting cancelled, and I am left with only 111. Okay, I am left with only 111. Yes. Yes. So I have 7 here, and then 2 zeros are cancelled with this 100. Okay, 112 is cancelled with this 12. So what do I have? This 12 is cancelled with this 3. So I have 22n is equal to 21n. Okay, and this is a perfect square. This is the nearest perfect square. This is the nearest perfect square. So see now, it has 3 and 7, right? It has 3 and 7, and it has 11 and 2. So obviously, this n, 22 will divide this n for sure. 22 will divide this n, right? 22 will divide this n for sure. And this perfect square will have 3 and 7. So obviously, if I simply assume it to be 441, and now I have to go nearer to 441 so that I have 22 with me. So what is 484 minus 22 is 462, right? So if I just simply write it as 462, if n is 462, right, then what do I have? Right, the nearer square is 440, 22 into 441, right? 441 is nearer. This is 21 and 21 2 is this. So n is 462. N is 462. This is pure hit and try. Do you see this is why 22 will divide n? See, like this is 22 and this is 21. So 22 cannot divide 22. 22 cannot divide 21. So obviously 22 has to divide this, right? So 4 square plus 6 square plus 2 square. It is 54. Right? It is 54. The answer is 54 here. Okay. Okay. Perfect. Now, a natural number n is said to be good if n is sum of r consecutive positive integers. For some r, just a second, what is this question? For some r cube 2, find the number of good numbers in the set 1 to 100. For some r greater than equal to 2. This is r greater than equal to 2. Right? A natural number n is said to be good if n is, just a second guys, just a second. Yes. Sorry guys, I got an urgent call. Okay, a natural number n is said to be good if it can be written as sum of r consecutive positive integer for some r greater than or equal to 2. Find the number of good numbers in the set 1 to 100. Right? Now, if you see, if I take r equal to 2, the minimum sum which I can generate is 3. Then next is 5. Next is 7. So all odd numbers are my, basically good numbers. Okay. So I can clearly see 1 and 2 are not good. 1 and 2 are not good. 1 and 2 cannot be generated like this. If I take r equal to 3, 1 plus 2 plus 3 is 6. 2 plus 3 plus 4 is 9. Now you can clearly see here, it is an AP with common difference 3. So 6, 9, 12. So you can see here that all the numbers are of the type 4k, in fact 6k can be generated. All multiples of 6. So see, like odd is anyway not a problem. So if I take r equal to 4, 1 plus 2 plus 3 plus 4 is 10, then 14, 18, 22, right, like this. Okay. So only numbers which will be missing are 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5 and 2 to the power 6. So these 7 numbers cannot be generated. So answer is 93. 100 minus 7 is 93. Only 2 to the power numbers cannot be generated like this. Sum of consecutive numbers. Okay. Sum of consecutive numbers. The answer is 90. Yes, Shubhajit Paul, you are right. Now moving on. 93 is the correct answer. Yes. Positive integers a, b, c satisfy ab upon a minus b equal to c. What is the largest possible value of a plus b plus c not exceeding 99? So see, like this question I solved. It is a very simple question. 1 by c is equal to 1 by b minus 1 by a. So basically you just have to write 1 by a plus 1 by b equal to 1 by c. In fact, 1 by a plus 1 by c, 1 by a plus 1 by c equal to 1 by b. Right? Okay. Now, I can see here that 1 by 3 plus 1 by 6 is 1 by 2. And that simply I have to multiply. This is 11. I have to multiply it by 9. So what am I getting here? 1 by 27 plus 1 by 54 is equal to 1 by 18. So what is a plus b plus c? It becomes 99, which is the maximum possible value which is allowed. So my answer is 99. My answer is 99. Okay. My answer is 99. Find the number of pairs AB of natural numbers such that B is a 3-digit number. A plus 1 divides B minus 1 and B divides A square plus A plus 2. Now, this is a quadratic equation question. To be honest, this is a quadratic equation question. Find the number of pairs AB of natural numbers such that B is a 3-digit number. A plus 1 divides B minus 1. Right? So, A plus 1 is equal to K times B minus 1. In fact, B minus 1 is K times A plus 1. And B divides, and A square plus A plus 2 is equal to K1B. Right? K1B. This is given to me. Okay. Now, what I will do here, A square plus A plus 2 minus K1B equal to 0. Right? And if I write B, in fact, I already have two variables here. Just a second. So if, let me write it as a square plus a plus 1 as one root minus 1 okay is k1b minus 2. This gives me a into a plus 1 is equal to k1b minus 2, right? Now I can see here, see like what a plus 1 divides b minus 1, right? So I am seeing here that a plus 1 divides this. So if I take this k1b minus 2 as multiple of, right, this is b minus 1, right? If I take it as b minus 1, some multiple of b minus 1, then I will be good to go. Nonetheless, I have b to be a 3-digit number, right? B is a 3-digit number. So see like how I did it, it is a square plus a plus 2 minus k1b is equal to 0, right? Right? Now let's eliminate b from here, right? So I have a square plus a plus 2 minus k1. What is b here? K into a plus 1 plus 1 equal to 0, right? Then I will have a square plus a. Now k1 k is another variable. It can be taken as k2 a minus k2 a plus 2 minus k1, right? 2 minus k1. Now this equation has integer roots. This equation has integer roots. So the discriminant will be perfect square. Discriminant will be a perfect square. This discriminant will be a perfect square, right? Right? So 1 minus k2 square minus 4 into 2 minus k1 is equal to q square. So basically, I think we should deal it in quadratic, right? I'll deal this in quadratic. When we do the pyqs of algebra, we'll do it there. Because this is a typical quadratic. No, this was not bonus. This was not bonus. We solved it, I remember. I distinctly remember us solving it, right? So we'll solve it in the quadratic. Okay, nonetheless, 42. Yes, this was another interesting problem. Greatest integer of n, greatest integer, square root, right? For any real number t, suppose that n is the greatest integer such that greatest integer of, what is it written here? Square root of is 4. Now this means that this is this value, square root of, we have to go very slow here, lies between 4 and 5, right? Which means greatest integer of lies between 16 and 25, right? Which gives me square root of greatest integer of root n to be between 16 and like my greatest integer can be 20 till 25. So this is it, and then I have to square it. So greatest integer of root n 256 625, right? So that again n is 16 to the power 4, 25 to the power 4. This is the number. Right? So my n max is 390624, which is this minus, just this minus 1. So what is the sum of digits of this? 12, 8, 24. 24 is the sum of digits. So see, like there was one particular year, I think this is the first year of IOQM, of the name IOQM. In fact, IOQM was in 2021 also. But in this paper, IOQM and INMO were together. There were some 7-8 problems of IOQM and it was ISI pattern. It was ISI pattern, right? It was ISI pattern of the format. Like it was of the format of ISI, in which there were 8 problems, 8-9 problems, objective problems, and then subjective problems because of COVID. Okay. Now IOQM 2023. Let's do this problem. Let n be a positive integer n such that n lies between 1 to 1000. Let mn be the number of integers in the set xn. Let a, mn, maximum and b is the minimum value. Find a minus b. Okay. N is a positive integer. Let mn be the number of integers in the set. Right? Okay. So for example, see, like if you take x1, you will have root 5, root 6 till square root of how much? Square root of 1004. Okay. This is your x1. Right? Let mn be the number of integers. Now, see, like basically we just have to take how many perfect squares are there, how many numbers we have in the perfect square. So let a is the maximum. Mn be the number of integers. Okay, got it. So see, like the maximum number of integers will be in this because it has a square root of 9 till a square root of 961. So it has 3, 4, 31. So these are 29 integers, right? The minimum will be in x thousand. X thousand. What is it? 4001. Because see, like the difference between consecutive perfect squares increases as we increase the number. And if you see, these are basically 1000 numbers. So now in these 1000 numbers, if you see, 4096 is perfect square of 64. Then 65 is 4225. 65. 66. What is 66 square? 66 square is 66 6 are 396. So this is 4 3. Doesn't matter actually. 38 69. 70 square is, this is 70 till 70. So it has till 64 till 70, right? Because 71 square is 70 square is 4900. 71 is 5041. 5041. So this is 7. So the maximum value will be 29. Minimum is 7. So 29 minus 7 is 22. Right? It is totally game on interpretation. How do you interpret this? Basically, you have to understand that behind these, under these square roots, there are 1000 consecutive numbers. So obviously, more perfect squares can be achieved by having smaller numbers here. So the smallest set will have most number of perfect squares, right? So 22 is the correct answer. This is log. Okay. So if you see properly, this is t, this is 6 by t is equal to 5. So t square minus 5t plus 6 is equal to 0. So t is equal to 2 and 3. What is t? Log b to the base a is 2 and 3. So a square is equal to b, or a cube is equal to b. We have to consider these. We have to consider these examples. And we have to take till 2023. So how many distinct cases will be there? right? 54 cases. We have to take these two cases into the consideration. Okay. Next. Okay. Now let alpha and beta, see, like we found that we observed there was one more problem like this in the previous session. Let alpha and beta be positive integers such that 16 by 37 alpha by beta 7 by 16, right? Find the smallest possible values of beta. So first of all, what you have to understand here is, right? What you have to understand here is 16 into 16, see, like 16 into 16 is 256. Now what is 37 times 7? 9, 259, right? 259. 37 times 7 is 259. Okay. Okay. So, see, like what I have to do, 16 beta minus 37 alpha is less than 0. I have to see like this, 16 beta minus 37 alpha is less than 0, and 16 alpha, just a second, no, 16 beta, yes, this is correct, 16 alpha minus 7 beta is less than 0. Okay, and alpha and beta are obviously positive integers, right? Alpha, beta are obviously positive integers. So, with this, I can say that beta, and we have to find minimum possible, beta is less than 37 alpha by 16. And here I am getting beta greater than 16 alpha by 7, right? So, let's assume that I take alpha to be 112, right? Then beta comes out to be greater than 256 in this case, and alpha beta comes out to be less than 259 in this case, right? So there will be a possible beta here, which is 257 for alpha equal to 112, right? For alpha equal to 112. But then there's a problem. There is a problem here. The problem is less than 0. The problem is, the answer is, in this case, see, like the answer is, now if I take beta to be 258 and alpha is 112, I can actually divide them to get how much? This becomes 129 and this becomes 56, right? 56 upon 129. This proportion will satisfy this, but this beta can be further reduced, right? This is 43 into 3. This is 8 into 7, right? Right? So beta, see, like beta is between 16 alpha by 7 to 37 alpha by 16. But how do we solve it? How do we solve it? How do we solve it like this? Then see, like we have to do hit and trial only. We don't have any other option. What will we do? 16 alpha minus 7 beta equals minus 1. We'll put this, right? Right? This is in this equation. And then 16 beta minus 37 alpha, we'll try to minimize. We'll try to minimize this. Now, this is again Bezout lemma. This is again Bezout lemma. This is odd. 16 alpha, just a second. I need this to be 1 minus 1, right? So, what am I getting here? 7, 14, 21, 28, 35, 42, 49. Yes. So if I take 16 times 3 minus 7 times 7, I will get minus 1. So 3 and 7 are one solutions. Okay, now look closely. The next solutions is when I add 7 here and I add 16 here. 23, right? So 10 and 23 are solutions. And also have a watch on this. This should be minimized in one of the solutions, right? So see, like, this is alpha, this is beta. If I am putting alpha equals 3 and beta equals 7, this is 112 minus this is 1. So this is a perfect solution, right? This is a perfect solution. Now, if I see here, 23 times 16, what is 23 times 16? 16 3s are 8, 16 2s are 32, 368. Now the difference is minus 2 here, right? I want it to be negative, right? My 16 beta minus 37 alpha should be negative. So this is acceptable. So if I somehow get minus 1 here, that will be my answer. If I somehow get minus 1 here, that will be my answer. Adding 7 more, 17 and 16 here, 39, right? So now 16 into beta is 39 times 16. So strange, man. 16 9s are 44, 16 3s are 48, 624, 37 7s are 17 7s are 629. So now this is becoming negative. I think this is the minimum case. 10 by 23 is the minimum case. You cannot have lesser difference than this. 10 by 23, I guess. Right? 10 by 23 is the minimum case. Because then your differences are increasing. Your differences are increasing if you see. Right? So minus 2 is the minimum case. So 10 by 23 is the answer. 46. Right? 23, like I said. Okay. Now, find the number of triples ABC of positive integers such that AB is prime. Okay. AB is prime. So A has to be 1, obviously. BC is product of 2 prime. ABC is what it is. Just a second. I think there is some interpretation problem here. ABC are digits, is it? ABC is a 3-digit number, right? ABC is product of A and B and C. This is a product, right? Now A into B is a prime, so obviously A or B has to be 1. Okay, A and B has to be 1. BC is product of 2 primes, so it means B and C will be prime, right? So A is definitely 1. B and C are prime number 1, B and prime number 2, right? So it will be 2 into 3, 2 into 5, 2 into 7, 2 into 11, 2 into 13, right? This is 1, 1, 2, 3, 4, 5. And BC can be exchanged. BC can be exchanged, I believe, because it's the order triplet. A is definitely 1, BC can be exchanged, right? BC can be exchanged. Right? So A is 1, B, P1, P2, correct. So 10 cases accordingly here. Then 3 into 5, 3 into 7, 4 cases here because it can be exchanged. So 14 triples here. And now when A is prime, B is 1. So then C becomes product of 2 primes, right? C becomes product of 2 primes. Okay. Okay. So then if A is 2, C can be 6, 10, because the product has to be less than 2, 14. C case is A. If A is 3, oh, their product is not divisible by any. So no prime number can be repeated. No prime number can be repeated. So if A is 2, C will be either 15, which is one case only. If A is 3, then C will be 10 and 14. Oh no, only 10. One case. Right? 2 into C is 30. 2 into 15, 30. Because 2 into 3 into 5. 2 into 3 into 5. In this case, there are two cases. Right? And then when A is 5, C is 6. One more case. So total 17 cases are coming. 17 cases are coming, I think. Yes, 17 is the correct answer. 17 is the correct answer. 17 is the correct answer. Okay. Now, what it is? A positive integer n has the property that m square is expressible. Now, this is very simple question, right? Okay. In integer, find the maximum possible value of mod m minus n. Right? So, we have to make it into a perfect square. So, can I write it like this? 4m square, 16n square, in fact 16. 16m square, 64n square minus 40n plus 256. Why I am doing this? Let me tell you. This is 8n whole square minus 2 into 16, right? This is 80. I have multiplied it by 16. 2 into 8n into 5 plus 25 plus 231. So this becomes 8n minus 5 whole square plus 231. Our whole aim is to represent it as difference of two squares. 231. Okay. Okay. Now this is 21 into 11. So 16m plus 8n minus 5 becomes 21. 16m minus 8n plus 5 becomes 11. If you add them, m becomes 1, n becomes how much? Oh, this was 4m, sorry. 4m square, right? 4m plus 8n minus 5 becomes 21. 4m minus 8n plus 5 becomes 11. If I subtract them, I am getting, if I add them, I am getting 8m equal to 32. So m equals 4. Then 8n minus 5 becomes 5, which gives me n, which is a fraction, which is not possible, obviously. So this becomes, if I take it as 33 into 7, let's take 33 into 7. Because the difference, what is their difference should be? Their difference should be of the type 8n plus 2, 8n plus 10, which is 8n plus 2. This difference is 26, which is 8n plus 2. Yes. So 4m plus 8n minus 5 equals 33. 4m minus 8n plus 5 equals 7. If you add them, 8m becomes 40, m becomes 5, 13, 20, 13, 18. Again, this is not acceptable. So we have to do hit and trial basically, right? We have to do hit and trial. Basically here, this is what it is, right? 7 into 11 into 3, this which is okay. So M. So see, like eventually M will be 10 and N will be -4, right? So this will be 14. Basically, you have to do hit and trial, different permutation and combinations, right? So 14 is the correct answer. Yes. Now let's do it. For n belongs to natural number, let Pn denote the product of digits in n and Sn denote the sum of digits in n. Consider the set A, n belongs to natural number, square free, and Sn is a proper divisor of Pn. Find the maximum possible number of digits of numbers in A, right? Now what it is written, for n belongs to n, let Pn denote the product of digits in n, Sn denote the sum of digits of n. Consider the set A, n belongs to natural number such that product is non-zero, which means no digit of n is 0, is square free, and it is square free. Okay, square free means it has no square divisor, so all digits are different. Basically, Sn is proper divisor of, sum of digit is proper divisor of Pn, right? Find the maximum possible number of digits in numbers in A. Hush. Maximum, see, like if it has, let's say, more than 5, 6, 7, 8, 9. This is the maximum possible number of digits which it can have, but still its product will have a square. So basically, we have to construct it. If I'm taking 1 here and I'm taking 2, let's assume, I cannot take 4, I cannot take 6, I cannot take 8, right? If I'm taking 3, I cannot take 9 as one of the digit because it is square free. It is square free, right? 1, 2, 3, 4. I can definitely take 7. I can definitely take 5. So 1, 2, 3, 5, 7. Yes. So basically all prime numbers I can take. Okay. Now what is the sum of digit of this number? It will be 1 plus 2 plus 3, 6. 6 plus 12 is 18. Right? But the problem is the product here. See, like the sum is becoming 18, which is okay. But the product is not divisible by 3. So this Sn will not divide this product. So we cannot have a 3 here. In fact, if I reduce 3 and take n 9 here, let's assume. What is the sum of digit now? What is the sum of digit now? 9, oh, it has to be square free. So it can be 3 only. Okay. So I think I will have to take only and only 4 digits. Right? 1, 2, 3, 6, 13. And I cannot take 7, 11, 13. So some permutation of this can be maximum. So I think 4 digits, right? I think 4 digits. I can take only 4 digits. One can be, oh, there can be infinite ones, right? There can be infinite ones, right? And 2, 3, 5, 7. So now let's do one thing. Find maximum possible number of digits and maximum possible number of digits. Okay. See, like the product is 18. If I take any this thing, so what is the product? 7 5s are 35. 35 6 are 210. Right? This is product. And if I keep on increasing 1 1 1 1 1s, right? Right? Now the product of digit is fixed, right? What can be the sum of digits? So now 105 can be the maximum sum of digit, right? So what is it? What is the sum here? 7 plus 5 is 12. 7 plus 5 is 12. 12 plus 6 is 18, right? I have 18 here, right? Now I can take, these are the 4 digits. See, what is it? 5 plus 12 is 17, sorry. So I can use 88 ones, so that my sum becomes 105. Sum of digit becomes 105. And 105 will then divide 210. So 88 ones plus 4 these digits. So it can have 92, maximum of 92 digits. Maximum of 92 digits it can have. It can have maximum of 92 digits. Right? Because it is a written proper divisor. So it cannot be 210. Sum of divisors, sum of digits cannot be 210. Okay. So 92 is the correct answer. Okay. So in the land of binary, the unit of currency is called ben, and currency notes are available in denomination 1, 2, 2 square, 2 cube, bens. The rules of the government of binary stipulate that one cannot use more than 2 notes of any one denomination in any transaction. For example, one can give a change of 2 bens in 2 ways. 2 1 ben notes or 1 2 ben note. For 5 ben, one can give 1 ben note and 1 4 ben note, or 1 ben note to using 5. Now this is, and 2 using 5 1 ben notes or 3 1 ben notes and 1 2 ben notes, or a 5 ben transaction is prohibited. Okay. So basically using 5 1 ben notes is impossible. 3 1 ben notes is impossible. 1 2 and 1 2 is prohibited because you cannot use more than 1, more than 2, right? Find number of ways in which one can give change of 100 bens without following the rules of government, right? So 100, obviously 64 plus 32 plus how much? 64 plus 32, 96 plus 4. Okay. So one can give 2 to the power 6, 2 to the power 5, 2 to the power 2, right? Now if somebody has to use 2 to the power 5, 2 to the power 5, 2 to the power 4, 2 to the power 4, this is also okay because you cannot use more than 2. So I have just used 2, 2 to the power 2, 2 to the power 5, 2 to the power 5, 2 to the power 4, no, sorry, 2 to the power 6, 2 to the power 4, 2 to the power 4, 2 to the power 1, 2 to the power 1. This is also 100 only, right? And then 2 to the power 6, 2 to the power 5, 2 to the power 1, 1, 1, right? 2 to the power 5. So yeah, it can have many cases, right? Like this. It can have many cases. I can clearly see, right? And we just have to manually count it. So in total there will be 19 cases, right? Basically you have to split powers into, right? 2 to the power 6 into 2, 2 to the power 5 into 2, 2 to the power 4 into 2, right? Like this. That is what you have to do. Okay. Okay. 19. Perfect. Now, a positive integer n greater than 1 is called beautiful if n can be written in one and only one a way as n this equal to this. For some positive integers a1, a2 this, where k is greater than 1. For example, 6 is beautiful because 6 is equal to 3 into 2 into 1, and this is unique. But s is not beautiful since, okay, find the largest beautiful number less than 100, right? Now this is pure hit and trial, right? So if you see, you can use 1 many times, right? So we'll start with 99. 99 can be written as, so what is 99? 9 into 11 into, see, like it can be written as 9 into 11 into 1 into 1. This is so many times so that the sum becomes 70 here. And but it can be written like this also, right? So there are two ways. So 99 cannot be represented like this. So basically, your number should be product of two prime numbers only. Two prime numbers only. 98 has 2 square, 7 square. 97 is single prime number, which is a problem, right? 97 is a single prime number, which is a problem, right? 96, obviously, 95 is the biggest number because 95 is product of two prime numbers. 95, yes. So 95 is product of two prime numbers. Okay. Now the last question. We are solving till 2023. Let dm denote the number of positive divisors of positive integer m if r is the number of integer for which this is sigma, this is odd, then find the number of digits of r, right? Okay, let's see. Now this sum is d1 plus d2 plus dn, right? Right? Now let's calculate S1. S1 is d1, which is 1. So r equal to 1 is okay. S2 is d1 plus d2. It has two divisors, 3. So r equal to 2 is okay. S3 is d1 plus d2 plus d3. Again, so r equal to 3 is okay. But when you see S4, 4 is a perfect square which has 3 divisors. So S4 is S3 plus 3, which is 8. And this is where the problem begins. This is where the problem begins. Now, if I add 5, 6, all these will be even. Why I am saying? Because see, like all perfect squares have odd number of divisors. So the parity will change. The parity will change when you have a perfect square, which means S9 will now be odd. So let's see. S1 is odd, S2 is odd, S3 is odd, S4 is odd, S4 is even, sorry. Then S9 is odd till S15, right? S16 is again even, right? So you have 3 here, then you have 7 here, then you have to write, you actually have to leave. So basically, see, there will be 3 odds, 5 evens, 7 odds, 9 evens, 11 odd, 13 evens, right? This is n less than equal to 2023. So basically, you have to find sum of this AP, right? You have to find sum of this AP, right? So the R becomes 990, 990 such numbers, and 990 means the sum of digit is 80. Okay, right? It becomes 80. Okay, now see, like there are 2024 problems. 2024 paper was very, very easy, right? So all these problems are homework for you, and you have to write the answers of all the problems. You can find the solutions of IOQM 2024 in our playlist, right? We have solved all the problems of 2024 this year only. This was very easy, IOQM. But why I am not solving it? I want you to solve it as a mock paper, right? So my humble request is, once you complete your IOQM syllabus, take this paper of IOQM 2024 and attempt it as a live paper. Then you will understand your level, how much you are getting in IOQM. Okay, so we'll again meet in the next class. Let's crack it.